Okay, so it's time to go ahead and begin. Looks like some people might have went home, huh? So I was right. See, I told you this streak was gonna end early. I did say that last time, right? In this class. Or maybe I said it in another class. That's typically what happens at the beginning, somebody caves. All right, so today's class, we're first gonna talk about what a universal gate is. Actually, two of the five gates that we've talked about, a NAND gate and NOR gate, are referred to as universal gates, and we'll talk about why that's so. And then so far we've talked about sum of products and product of sums. And lab one, okay, the lockbox lab, right now, you can do two of the outputs. You can have an SOP output and a POS. And remember, we want those outputs to be the reduced expressions, right? So just like we talked about last time, you gotta do a K-map and get the reduced SOP and also the reduced POS. And that's the two equations that you would use in a sign statement in your Verilog design file. Okay, remember lab 0 just had the one assigned statement because you just had one equation. But for lab 1, you're going to have two assigned statements because we got two equations. So you might want to call one output, like F underscore SOP, and the other output like F underscore POS. Okay. And remember, those equations came from the same truth table, so logically they're equivalent. So one of the things you're checking for when you're doing lab 1 is that both outputs are giving you the same output for each of the 16 combinations. Okay, so the outputs should be in sync with each other. Okay. Well, today we're going to talk about two other digital type circuits. One is called NAND, and the other one's called NOR. And to complete lab 1, you add a third output. So you'll have SOP, POS, and you'll also have a NOR output. So you'll eventually have three outputs, so three equations. Okay, and I think lab 1 is due this Friday, if I remember right. Okay, and after today's class, you'll be able to complete lab 1. Okay, and there's an activity also that I have on NAND, and NOR. All right, that's sort of what the game plan is today. So where we're going to start is with universal gates. So as I mentioned right at the top, of the five gates that we've talked about, we talked about a NOT, an AND, an OR, a NAND, and a NOR. Well, out of those five gates, two of them, the NAND and the NOR, are called universal gates. And the reason they're called universal gates is because you can make all other gates out of universal gates. So you'll see that with the NAND, we can make a NOT. With the NAND, we can make an AND. With the NAND, we can make an OR. And with the NAND, we can make a NOR. Okay, and same thing with the NOR. With the NOR, you can make a NOT. With the NOR, you can make an AND. With the NOR, you can make an OR. And with the NOR, you can make an AND. Okay. I'm going to show you how you use a NAND to make the other gates. And then part of the activity is for you to show me how you can use a NOR to make the other gate. Okay, so if you understand what I do up at the board here with the NAND case, you should be able to figure out the NOR case during the activity. So first of all, okay, to understand how this is done, you have to refer back to the truth table for the particular gate. Here is the NAND that we're going to use in class. Here's the NOR that you'll use for the activity. So you may recall that with the NAND gate, you only get a 0 out when all the inputs are 1. Right? It just takes one of the inputs, at least one of the inputs, to be a 0 to get a 1 out of an AND. And again, it doesn't matter how many inputs you have, the same concept is true. Okay, well, there's actually two different ways to come up with having a NAND gate act like a NOT gate. And remember, a NOT gate, you just get the opposite out of what's going into it. So one way that you can see that a NAND can be used as a NOT is that if I divide this truth table in half, okay? And then I only look at the bottom two rows. So just pretend the top two rows aren't there. If you just look at the bottom two rows, can you see what these bottom two rows tell us? That if we make an input to a NAND gate a 1, right? So if we connect one input to a NAND gate as a 1, if I take a NAND gate and I connect one of the inputs directly to a 1, so it's a 1 all the time. We'll look at how the other input relates to the output. If one input is a 1 and the other output is a 0, I get a 1 out. If one input is a 1 and the other input is a 1, I get a 0 out. So you see, if I make one of the inputs to a NAND gate a 1, whatever that other input is, if I call that other input B, the output's going to be not B, right? Because again, see, B is 0, output is 1, B is 1, output is 0. Okay, so you see, that's one way that you can configure a NAND gate to be a NOT gate. Just connect one input to a 1, and the output will just be the inverse of the other input. Okay, so any questions on what I did here? Does that make sense to people? It's just understanding the truth table. Okay, there's another way. Okay, so there's a second way that I can connect a NAND gate to be a NOT gate. Okay, and the other way to do it is just look at the top row and the bottom row. Okay, so just ignore the middle of the truth table. But look, if you just look at the top and the bottom row, the top row, if I make both inputs 0, the output's going to be a 1. The bottom row, if I make both inputs 1, the output's going to be 0. Well, again, that's a NOT gate, right? If you're getting the opposite out of what you're putting in. Now, how many people have had circuits? Have like circuits one? Okay, most people. Okay, if you've had circuits, and remember, the 1s and 0s are just voltages, right? Ideally a 0 is 0 volts, ideally a 1 is like plus 5 volts. If you have a circuit and you want to make like 2 nodes in that circuit the same voltage, like they have a node over here and you have a different node over here, right? Remember, nodes are connections, right? If I want to make them the same voltage, what do I do? Say it again. Well, what would you have to do to put them in parallel? Short them, exactly. If you take a wire and you go from this node to the other node, it's going to make the voltage the same, right? Because voltage is the same along the same node, right? So it's the same thing here. I can just do this. Here I've got my 2 inputs, right? If I short them together, it effectively makes it the same node and they got to have the same voltage, right? If I connect these two inputs together, they can only be both 0 or both 1. There's no way if I connect 2 inputs together that one input can be a 1 and one input can be a 0. Right? I mean, what happens in a circuit if you connect 5 volts and ground to the same node? What's going to happen? What's the best case that's going to happen to your power supply? If you take one end of the power supply and you go to the same node as ground of the power supply. Because what are you doing there? What are you doing to the power supply? If you connect the plus, yeah, you're shorting the power supply. Right? So best case scenario is the fuse blows. Worst case scenario is you burn something up, right? So if you connect 2 things together, it forces it to be the same voltage. And here, remember, the 0s just represent 0 voltage and the 1s just represent some plus amount of voltage. Okay? So you see, these are 2 different ways that you can make a NAND gate into a NOT gate. As you call this input, you're going to get the opposite out. Okay? So any questions on either one of these, how these work? All right. So now let's talk about how you can use a NAND gate to make an AND gate. All right, well, that goes back to something we talked about when we first talked about an AND. You remember what NAND is short for? Not AND. And why is it called not AND? So what is the NAND gate equivalent to? What could I, how could I make a NAND gate with like two other gates? What is it? In fact, it's with this little bubble in place. Say again? Put the knot where? The little bubble does indicate it. Not for an and. Yeah, just an and with the knot where. Yeah, on the up, that's what I was looking. Right, so a NOT gate, remember, that's what that little bubble is telling us. The little bubble is telling us that the NAND is an AND with an inverter on the output. See, it's equivalent to this. Okay? All right, well, knowing now that I can make an inverter with an AND gate, if I take a NAND, okay, which you just told me was equal to an AND with an inverter on the output. Now, if I put an inverter, a NAND gate that's connected as an inverter, so if I take a NAND and say I use this, I could use either one of these, but say I use the one where I connect one input to a one, like that. Well, this here, right, this AND with the inverter on the output, that's equivalent to this NAND. And now if I put an inverter here, right, this NAND is an inverter. Well, what happens if you put two inverters in a row? Yeah, they cancel out, right? So this would just cancel out and it's equal to an AND. So you see, if I take a NAND gate and I put another NAND gate that's acting like an inverter, well, this all together is going to give me an AND gate. The one is what we did here, just that one way to make a NAND into an inverter is to connect one input to a one. Because like we said, if you look at the truth table, if we look at the bottom two rows, right, if I make one input to an AND gate a one, the output's gonna be opposite the other input. Okay, I mean, the other thing I could do is I could do this, I could use the other type of inverter. Right, because you can also make an inverter with an AND gate like this, so either one of these be an AND gate together. Okay, so does everybody see that? All right, now let's talk about how we can make a NAND into an OR. Now this goes back to De Morgan's theorem. Remember De Morgan's? Right, there's two parts of De Morgan's. One part of De Morgan's tells us that a NAND is equal to what? OR. Okay, well, you're right that there's an OR and there's a NOT involved, but where are the NOTs? We have an OR gate. Right, yeah, exactly. This is one. Yeah, so one part of De Morgan tells us that a NAND is equal to an OR gate with inverted inputs. Okay, so if I draw this, I draw a NAND like this, you can think of it like this, that it has an OR, it's the same as an OR. Oops, not a NOR. Don't want the bubble there. Equal to an OR with inverted inputs. Right? So this symbol is the same as this. Well, what if I do this? What if I put NAND gate as inverters? And again, just to drive home that there's two ways to make an AND gate to inverter. I'll make one with shorting the inputs together, and I'll make the other one with putting one. Say that again? Oh, okay, like, is there any preference between these two? Not that I know of, I think it's pretty much just personal preference. In a lot of cases, I think it's probably easiest to do this, because it's just taking a wire, connecting the two inputs together. Here, you know, you'd have to have a wire going to like a power supply or a power source or something, so, yeah, but most of the time there's no real difference for me, it's just personal preference really. But can you see that since this NAND gate is equal to an inverter with, an OR gate with inverted inputs, if I add two NAND gates that are inverters on the input of this NAND gate, that's effectively canceling out the inverters on the input, and I'm just left with an OR. Okay, does that make sense? All right, well, if that made sense, and if, when we talked about the NAND being a not AND, this coming up should make sense, using a NAND as a NOR, because what is NOR short for? Not OR. Wobbly wheel on the table. Right, NOR is short for NOR, not OR. We already have NAND as an OR, right? Because that's what this is up here. Oops. Right, so this right here is the same as an OR gate. Right, because that's what we did right up here. Right, so if this is the same as an OR gate and I want to make a NOR, what would you do? And NOR means not OR. Yeah, just put a NAND gate as an inverter on the output. So again, you could do either one of those. You see now this all together would be a NOR. Okay, so you see, to make a NOT gate out of an AND, you need one NOT gate, right? And there's two ways to connect them. To make an AND, to make an AND out of an AND, you would need two NAND. To make an OR out of a NAND, you need three, and to make a NOR, four. Okay. Now, you know, you're probably wondering, well, why do this? Why is this a big deal? Well, this used to be a bigger deal, you know, back in the day, you know, back when I took a class like this, or maybe up until about like 20 years ago or so. Because, you know, around 20 years ago or so, that's when they started coming out with programmable ICs like the FPGA that's on your basis board. Okay, remember FPGA, it stands for Field Programmable Gate Array. And like I explained on the first day of class, the way you can think of that FPGA is that sort of like a silicon breadboard, if you will, right? There's logic blocks in there that you can think of like as components, and the interconnects between the logic blocks are programmable. So when you write Verilog code, you're selecting out, you know, what parts of that silicon circuitry you want, along with how it's all connected, instead of doing it manually like you do in an analog lab, like in your circuits 1 or circuits 2 or circuits 3 lab. Okay. Well, you know, back when I took this class, and like I said, up until about 20 years ago, those type of ICs, those FPGAs, they didn't exist. So you would have individual ICs, and these individual ICs would only have one type of gate on them. Like you could buy an IC and it only had inverters. You could buy an IC, only had NAND gates, only have OR gates, and so on. Well, if you could do your design all in one gate, that means your purchasing department would only have to buy that one type of gate. They wouldn't have to buy several different types of gates. And if you only had to buy one type of IC that had, like NAND gates on it, well, you could get a good price. Your purchasing department could buy in bulk, and that would drive the product price down. So, that used to be a big deal back in the day. Now it's not such a big deal because, like I said, they've got these programmable ICs. However, where this still is useful to know is actually at the silicon level, like when they make an actual IC, like the actual silicon circuitry that's in the IC. And I know EEs, how many EEs are in the class? Yeah, it's mostly EEs this quarter. You take, what is it, the 113, EE 113, and they talk a little bit about manufacturing in that class, don't they? You see the Silicon Run video, right, with how they make the ICs with the silicon. You see the big silicon nugget thing, or well, at that level, at the silicon level, it's useful to have one gate for your entire circuitry, because then you only need one image. You know how they use the photo tool and they shine the UV light, right, to harden the photoresist, and they etch it away and all that kind of stuff. Well, if you only have one type of gate, that's only one kind of image, right? It's not like several images. So again, it leads to lower, lower manufacturing costs. Okay. All right. So now, like I said, I went over how to use a NAND gate with all these different gates, right? Not, and, or, nor. Part of the activity is I want you to go through the same thought process, but instead use a NOR gate. So there's two ways to hook up a NOR gate as a NOT. You can hook up NOR gate with an AND, NOR gate with an OR, and NOR gate with an AND. Okay, so you're gonna do that as part of the activity. All right, so before we move on and do some more things here, we're gonna talk about NAND, and NOR. Are there any questions up to this point? Does everybody get universal gates? All right, so the rest of the class, we're gonna learn two other digital circuitry. One's called NAND, the other one's called NOR. But before we do, I just want to review real quick SOP and POS. This is the SOP equation that we had from that example with the eggs and the salts and the chips. And I just want to review what an SOP diagram would look like. What kind of gates would we have in an SOP diagram? Like, how are we going to get these terms? What kind of gate is it going to take? For each one of these terms, like, how do I get this? Not C, G, not F. What kind of gate am I going to need to get that term? NAND, right? Because these inputs, not C, G, and not F, they're just all AND together. So, right, we have the three inputs coming in, not C, S, right? And each term is going to have an AND gate. If you look back in your notes, we did that previously. So I'm not going to write in all the variables here, but you can do that. All right, so it's going to take an AND gate for each term. And then how do we OR them all together? How do we OR all the terms together? What kind of gate? Yeah, just a single OR gate, right? Right, so any SOP is going to have multiple AND gates, right? Because you need AND gates to get the terms, and then it's just going to have a single OR gate, because then you got to OR all the terms together. So this is where output E is going to be, right? That equation. Okay, so everybody remember that? We went over that before. It's just I'm reminding you of it because it's going to lead to something else here coming up. All right, how about product of sums? What's a product of sum circuit going to look like? What kind of gates are we going to have there? It's going to be multiple OR gates, right, to get each of the terms. Not very good OR gates, but make this one a little bit better. That one doesn't work so good. Right, so each one of these OR gates will give us a term. Okay, and then what are we going to have here? Right, and it's all going to go into a single AND. Right, so your POS diagram is just the opposite of your SOP, right? Okay, so everybody recall that? I mean, it was a couple classes ago. Main reason I'm putting those back up here is because I want you to compare NAND, NAND, and NOR, NOR to those once we know what NAND, NAND, and NOR, NOR are. Okay? All right, so let's go ahead and talk about NAND, NAND, and NOR, NOR. So I'm going to show you first how to get NAND, NAND from an SOP equation. Then I'm going to show you how to get a NOR, NOR from a POS equation. Then we're going to do a couple of examples. One's going to be NAND, NAND to POS, and one's going to be NOR, NOR to SOP. What you're going to see is that when you go NAND, NAND to SOP, or the other way, go SOP to NAND, NAND, that's fairly, relatively easy. Again, when you're first learning something, I know it's never easy, but relative to other things, it's fairly easy. And same thing, NOR, NOR to POS, or POS to NOR, NOR, fairly, move the camera, thank you. Not too bad. But when you go NAND, NAND to POS, or NOR, NOR to SOP, that's when you have to do some work. Okay, that's when it's not so easy. All right, let's see where we have to go here. There should work. I'm gonna have to move the camera in. Let's see, we'll put it right there, and then when I get over to here. So if I forget, please remind me. All right, so let's start right here. So if we want to take this SOP equation and get NAND, NAND, the first thing we're going to do is double knot both sides. Okay, so double knot here, and then double knot. Okay. All right, well, what do you think? If I take a variable and I double knot it, what do you think that's equal to? Yeah, just the original, because it's like passing that through two inverters, right? It's like taking E, putting it through an inverter, making it not E, and then putting it through another inverter, making it back to E. Right? So the double knot of a variable like this is just going to be equal to the variable. Okay. All right, but now what we're going to do, and we're going to do this because we want to get NAND, NAND. Okay. We're just going to look at this part of the equation on this side of the equal sign. We're just looking at the bottom bar and everything below it. We're not paying attention to this dot bar. Okay. So we're just looking at, this right here, this part of this equation. So if you just look at that part, it's this term, or together with this term, or together with this term, or together with this term, the whole thing not. So if you take each one of these terms as an input, this is an input. This is an input. This is an input. This is an input. You have 4 inputs being ORed together, and then the whole thing not. Well, what kind of gate is that? If you got 4 inputs coming in, they're getting ORed, and then they're getting knotted after that, that's a what? The NOR gate. So you see, this is a NOR gate. Will represent the NOR gate with inputs, not C, G, not S, not C, G, S, C, not G, not S, and C, not G, S. And what does De Morgan tell us about a NOR gate? Now, we talked earlier that De Morgan tells us that an AND gate is equal to an OR gate with inverted inputs, but that's only one part of De Morgan's, right? The other part of De Morgan's tells us that a NOR gate is equal to what? An AND gate with inverted inputs. Okay, so that's what we're going to do here. We're going to take each input, invert it, and then AND it. Okay, so we'll have not C, G, F, the whole thing inverted. Then we're gonna AND it with not C, G, F, the whole thing inverted. We're gonna AND it with, if I make a mistake, please correct me. C, not G, not F, the whole thing inverted. Then we're gonna AND it with C, not G, F, the whole thing inverted. So that's just the bar with everything below it being a NOR gate equal to the input inverted all ANDed together. And then remember, this top bar wasn't part of this transformation, so that's still there. That top bar is still there. So after we double knot both sides and then do De Morgan's once, look what we have. We have this input, this input, this input, all ANDed together, the whole thing inverted. Right? This input, this input, this input, all ANDed together, the whole thing inverted. This input, this input, this input, ANDed, the whole thing inverted. This input, this input, this input, all ANDed, the whole thing inverted. So each one of these terms is what kind of gate? A NAND, right? Because each one of these terms, you're ANDing the variables together and then inverting the whole thing. So each term is a NAND. And then we're taking each NAND, ANDing them together, and inverting the whole thing. So it's another NAND. See, that's why it's called NAND NAND, because unlike SOP and POF, where you got different gates, right? You got ANDs and then an OR, and here you got ORs and then an AND. NAND NAND, you'll have NANDs and then an AND. See, the diagram for this would be 4 NAND gates. Four NAND gates. All going into another NAND gate. Right? So that's why it's called NAND NAND. Right? Just using NAND gates. Multiple NAND gates going into a single NAND gate. All right, so you have any questions on that? Because if this made sense, NOR is going to make sense because it's very similar. It's just you're using NOR gates instead of NANDs. Does that make sense? So you good? All right. Well, let me show you how to get NOR. Before I show you how to go NOR to POS. Also, look how easy it is to go from NAND back to SOP. Because if we go back to what we originally had. Okay, so let me get rid of all this. See, to go from NAND to SOP, all you got to do is take the terms underneath the bars, right? So you take, not C, G, not S, and not C, G, F, C, not G, not F, C, not G, F. Take those terms and just OR them together, right? See how that term ORed with that term, ORed with that term, ORed with that term. Okay, so once you have NAND to go to SOP, it's just basically getting rid of the bars and just ORing all the terms together. Okay? All right, so let me show you how to get NOR from POS. Well, just like we did in the previous derivation, we double knot both sides. This is just going to be E. And we're just looking at the bottom bar and everything below it. Again, we're not looking at the top bar. So if you just look at this part of the expression, the bottom bar with everything below it, and you take this as an input here, each term is an input. All right, this input, ANDed with this input, ANDed with this input, ANDed with this input, the whole thing inverted, right? So that's what kind of gate. You're ANDing everything, then inverting everything. It's what kind of gate? Well, NOR, you got to be ORing things together. NAND, yeah, the NAND. So this is a NAND with inputs that you see here, right? The, you know, the C or G or F and so on. I'm not gonna write them all in. You can write them in these four. And what does the Morgans tell us about an AND gate?
Equal to or here.
Exactly, it's equal to an OR with inverted inputs. So I take each one of these inputs, invert it, and then OR it with connect. Right, so see, that's the expression, the bar and everything below it, right? Being a NAND is gonna be equal to each one of these inputs inverted and ORed. And then again, we still got the top bar there. So this top bar is still there. Right, so now when you look at this, you have inputs ORed together, it's the whole thing inverted. Inputs ORed together, the whole thing inverted. Inputs ORed together, the whole thing inverted. Inputs ORed together, the whole thing inverted. Right, so these terms are NOR gates. NOR. And then those NOR gates are ORed together, the whole thing inverted. So you see now we have all NOR gates, right? Because each term is a NOR gate. Term is a NOR gate. And then we got a single NOR gate that all these feed into. Okay. And, you know, all these different forms here, as long as they come from the same truth table, right? SOP, POS, NOR, NAND, they're all logically equivalent. Okay, so in your lab one, as I said towards the beginning, based on last lecture, you could come up with reduced SOP, reduced POS. Based on this lecture, you'll be able to come up with the reduced NOR. Because once you have the reduced POS, to get the reduced NOR, you just do this.
How would you code all the knots, or would you simplify that part?
Are you talking about like these terms here?
Yeah, because would you just do not C?
Well, in Verilog, like to do this term here, like say you want to do this term, I would just put in parentheses, I would just put, you know, it'd be like C, whoops. It would just be C ORed with G ORed with S, and then you put the tilde outside the parentheses. That would give you this term. And then like if you had, say you're doing this term where you had C ORed with G ORed with not S, that would just, you know, you just put a not S.
Or what about the extra not?
Oh, well then, well, that's just for a term. Then you'd have to OR all the terms together, have another parenthesis, yeah, like put the whole thing within parentheses and then put a tilde, and that would not the whole thing. So yeah, you'd have to use parentheses, so it, you know, it basically works in outward, yeah. You know, just like when you do a base 10 equation. Okay? Any other questions up to this point? We got, it'll probably only take me another like 20 minutes to finish, so unless there's any strong objections, I won't take a break at the top of the hour, I'll just go and finish, and that way, you know, I'll be done with the lecture part, and you can work on your activity, and then, lab one after that. Okay, but like I said, either one of these, NAND to SOP, or SOP to NAND, NOR to POS, or the other direction, because if you go the other direction, right, POS to NOR, again, if we go back to what we originally had, See, to go from nor back to POS, you just take what's underneath the bars, right? These are your terms, and you just and them together. So you just take like C or G or S, and it with this term, and it with this term, and it with this term. Okay? All right. Now, the next two examples, NAND to POS and NOR to SOP, that requires more work. Okay? It requires more work than these do. Because in order to go NAND to POS or NOR to SOP, you have to either go through a K-map or a truth table. I'm going to show you the K-map way because that's something we just learned about, right, last class. And plus, you typically want the most reduced expression, right? And remember, in this class, when you hear the word, the phrase reduced expression, we're talking K-map, right? Because that's how we reduce expression. Okay, so I think the best way to learn these methods is just through an example. So first, I'm going to show you how to go from NAND to POS. So here's a NAND equation, and in order to go into a K-map, now, last class, we saw how to go from a truth table to a K-map or from an expression, right, a Boolean expression to a K-map. In what form were those equations? When we went from a Boolean equation into a K-map, did we have SOP or POS? And in fact, even when you're going either from a truth table or into a truth table, do you want a POS equation or an SOP? What's easier to deal with? SOP, exactly. So that's what we want to do here first, is we want to take this NAND, make it SOP, because then I can go into K-map easily. Okay? So as I was saying before, if you look at our example here, to go from NAND to SOP, you're just taking what's underneath the bars and just pouring them together, right? So you can see this would just be, the SOP for F. This is SOP for F. It's just going to be AC ORed with not CD, ORed with not A, B, not C. See, I'm just taking what's underneath the bars and just pouring them together. Okay? All right, so now we're going to put this expression into the K-map. And since it's SOP for F, are these terms going to give me groups of ones or groups of zeros? Ones, right? Because ones go with F, right? Zeros go with not F, right? All right, so you see we're just going the other direction now. Last class, when you did K-maps, you were getting the reduced expression from the K-map, right? The K-map was filled out first, and you got the reduced expression from that. Here, you're taking an expression, an equation, and you're filling out the K-map, right? So you're just doing it like in reverse order from what we did last time, okay? So what group of ones is this AC term coming from?
15, 14, 10,
Okay, say that again.
15, 14, 11, and 10.
11 and 10. Everyone agree? Yeah, because that four grouping, it's all in A and it's all in C. So that one's taken care of. How about not CD? Where would the ones go there? Say it again.
12, and, I'm sorry, no, 13.
13 and 9, is that all? Because remember, it's
about 1 5.
oh, yeah, okay, very good, yeah, because remember, a 2 variable term in a 16 cell, that's a 4 grouping. So you have 4 ones. So yeah, see how this column here, it's all in the D and all in the not C. All right, now we have not A, B, not C. So first of all, what number grouping is that? Since it's a 3 variable term in a 16 cell, 2, right? So which 2 cells would give us not A, B, not C? 6 and 7? Any other? 4 and 5,
No,
4 and 8? How many people say 4 and 8? You changed your answer? What did you change it to? Okay, 4 and 0? 4 and 5? What was the other one? There was another one. It was 4 and 8. How about? Don't know? Any honest people out there? Oh, an honest person. How many people don't like raising their hand? Have I done this already?
Yeah.
Okay, can't catch anybody anymore. I think it's 4 and 5, isn't it? Because 4 and 5, okay, we're looking just at this 2 grouping. Not A is common to that 2 grouping. Not C is common to that 2 grouping, and B is common to that 2 grouping. What's changing is D. See how D is changing? Because cell 4 is in not D and cell 5 is in D. So remember what changes gets dropped out. Okay. All right. So now we have all the ones where they're supposed to go. So wherever there's not a 1, there's a 0. Let's put our zeros here. Okay, and now the next step, since we're after POS, you should be able to tell me what the next step is. Because if we want POS for F, right, we want POS for F, we need to get what first? Okay, because that will give us what? What kind of equation will that give us? Not F, SOP, right? Yeah, we want to get SOP for not F, right? Because once I have SOP for not F, I can do De Morgan twice to get POS for F. Right, and again, De Morgan twice, that's when you flip everything, and to ors to ands. And then once we have POS for F, what can I easily get? Well, something we can easily get that we did earlier, and that we could get nor, right? Because once you have POS, you could then easily get nor from what we did here. Okay, all right, but let's group the zeros. So how would you group the zeros? Where would you start?
Top right, 1.
Yeah, this looks good here, right? These 4. And what term is that going to give us? Not AC, everybody agree? Because that 4 grouping, it's all in not A and all in C. So yeah, I agree, not AC. Okay, what would you do next? 0 and 2. There's actually more than one correct solution to this, right? Because you could group 0 and 2, or you could do 0 and 8. We'll do 0 and 2. Well, what's that going to give us? Does it give us an A term? Not A? Not B?
Not B.
Not B, then what? Wait, remember, this has to be 3 variables, right? Because what's the next one?
Not B.
Not D, right? Because C changes, right? Because this one's in C, this one's in not C. So it'd be not D. All right, and then what would you do next? 12 and 8? 12 and 8. That's going to give us another 3 variable term. So what's it going to be? A, not C, not D. Right, yeah, because B changes, right? This is in B, this is in not B. So. All right, and then to get POS for F, that's when you do De Morgan's, everything inverts. And ands to ors and ors to ands. So it's gonna look like this, right? again, if I make a mistake, let me know. I think I didn't make a mistake. Always good to double check. Right, and like I said, if you then wanted to go to nor, you could just do what we did here to get nor from this POS. Okay? All right, so any questions on this example? See, this is a good example at this point, right? Because it's introducing something new at the same time you're learning or reviewing stuff we've gone over before, right? Because we've done K-map, we've done FOP to POS before, so it's some review too, besides new stuff. All right, one more example before you can start working on your assignments. And this is going nor to SOP. So here we have our nor, and to go from nor to POS, well, like I said earlier, that's pretty easy, right? Because you just take what's underneath the bars and you just and them together, right? So you take the terms underneath the bars. So this is going to be F POS. So we're just going to take A or C, right? This term here, and then end it with not B or E. Oh, question? Oh, move the camera. Yeah, see? If I don't have somebody remind me, I forget, so thank you. There we go. All right. Yeah, thanks again. All right, so this got a POS for F. Now we want to fill in this K-map. But to fill in the K-map, what type of expression do we want? What's easier to fill out a K-map or a truth table than POS? SOP. So I want to get SOP from this. So what do you do when you want to go from POS to SOP? Invert everything. What else? And so, or the worst end, right? You're just doing De Morgan's twice again. Remember, you can go SOP to POS or POS to SOP by just inverting everything, ands to ors to ands. So De Morgan's twice, that's going to give us SOP for not F. And it's going to be not A, not C, ORed with B, not D. Right? Again, double check what I'm doing, make sure I didn't make a mistake. I inverted everything, right? I ANDed the A and the C, the B and the D, and I ORed them, right? So this is SOP for not F. Everybody agree I didn't make a mistake? All right, so now, what am I gonna fill in to the K-map with a not F expression like this? 0. Okay, so where are the zeros gonna go for this term? Not A, not C. Which one? These down here? Is that, for which one is that?
It's a real.
Oh. So up here, 0, 1, 4, 5, you said? Okay. Yeah, everybody agree? Because those are in the not A, not B. All right, how about B, not D? Oh, so the 0 is gonna go in there.
6, 14, 4.
Yeah. 6, 14, 4, and 12, right? Because that 4 grouping is all in B and all in not D. All right, so where you don't have a 0, you have a 1. So fill in the 1s. And now, by circling the 1s, we're going to get the reduced SOP for F. And then once you have SOP for F, you could get the NaN expression, right? You could go from this to NaN if you wanted to. I mean, we weren't asked to do that, but I'm just pointing that out in what we did earlier. Okay, but anyway, now we got to group the 1s together. So what are we going to do there? Do you want to group?
A row on the bottom, 8, 9, 11, 10.
Okay, along the bottom here. Okay, what term is that grouping gonna give us? Yep, A not B, yep, I agree. Okay, what do you wanna do next? Okay, we could do this, because remember, you can overlap, right? This four grouping, what is that gonna give us, what term? AD? Okay, what do you wanna do next?
37, 15, 11.
All right, we can do this column here, another four grouping. What term is that? BD. All right, so what do we got left?
3, 2, 11, 10.
Very good. Right, we can take this single one and make it part of a four grouping, because again, the top and the bottom touch and you can overlap. So this four grouping. What term? Not BC. Okay, so you see that's our reduced SOP graph, and like I said, you could then do what we did over there to get NAND if you wanted to. Okay, but the thing to take from this again, NAND, SOP, not so hard, NOR, POS, not so hard, but when you gotta go NAND to POS, or you gotta go NOR to SOP, you have to go through a truth table. Right, and that's when you're using, you know, things you learned earlier last week. Okay, so this is a good type of review problem. You know, the activity that you have today, you have to do much of what I went over at the board. So if you have a good understanding of today's activity, I would say that that's a good sign for this part of the class that you're, you know, it seems like you're up to speed. Okay, I just want to say a few more things about the labs. Well, first of all, my solution to the activities up here, and I'll pass out the activity in just a second. But I just want to stress, lab one, your high-level black box diagram, okay, which again gives you the main inputs and the main outputs. You have 4 inputs, right? Remember, this is a black box, and it's only going to open for 9 of the 16 combinations. Okay, and these are the input names that we have. Well, you're going to have 3 outputs. You're going to have an SOP output, a POS output, and a NOR output. Again, these all should be reduced. Part of the lab is to compare your elaborated design that you get from your modeling to a schematic that's provided. And it should have the same number of gates. I think there's 12 gates. If your design works, okay, like if your design for each one of these outputs gives the correct truth table, and remember, these expressions are logically equivalent. So your outputs should all be in sync. When you simulate this design, those 3 outputs should be 1 at the same time. They should be 0 at the same time, right? They should all be in sync. When you test it on the board, on your basis board, you're going to have 3 LEDs, an LED for each output. Those LEDs should all be in step. They should all be on, and follow the same truth table, okay? But what has happened in the past, if someone's not careful, is that they don't have a reduced expression like they think they do, but they don't. And one way that you can identify if you don't have the correct reduced expression is you'll get more gates in your schematic than what you should. So when you look at your elaborated design schematic, if you have more than the gates that are on the handout that you're given, which I believe is 12, but again, count them to make sure. You know, if it's supposed to be 12 and you've got 15, most likely one of your expressions is not reduced. Okay, so keep an eye out for that, because in the past, people have missed that. And, you know, you would lose points on your score if that's true, because you don't have the most reduced design. Okay? All right, so I'm going to pass out the activity. If you want to take a break before you start, you know, go ahead. But the rest of the class time is yours to work on the activity and to work on the lab. And once you get to the lab portion, like previous classes, if you don't want to stay here, you can go somewhere all the time. That's okay. Yeah, this activity, the first problem, it has an output with a dash. What does the dash mean? You remember what a dash means? Right, so don't care. You can make it a 0, 1, whatever's gonna lead to the most reduced expression. Okay, so everybody has an activity. I didn't miss anybody? Is Eric here? Eric Guzman? The Ivan Madrano? The Marvin? Yeah, I think some people went home, huh? I thought the strike was gonna be the whole week, or they were hoping.